Yes. Okay. Welcome everybody to the afternoon edition of our workshop. We start off with Mark Watkins talking about Sympow.
Okay, thank you. So this is supposedly called a status report. So I wrote Sympow before really Sage got started much, and well, Sympow was a project to write a paper, and basically we were trying to do such things as find evidence about symmetric powers of elliptic curves. One of the main things we tried to do was test modularity. This is now been proven. So I'd say the thing that needs to be done with Sympow is some of the functionality be taken out of it, actually. Okay, so what does Sympow do? So it takes an elliptic curve defined over Q, takes a positive integer, and it will compute the special L value, either at the center of the critical strip for M odd, or the edge for M even. So I've told you exactly what the center and the edge are. I'll state the exact functional equation later. It relates S to M plus 1 minus S, so in the M equals 1 case. That's the standard curve, of course. And it can compute these to 64 digits of precision. So this is just a convenience because I've used Bailey's quad double package. You could ask for more precision if you particularly wanted to, but then you have to implement it yourself. So of course, in some cases, so these the central values can vanish for reasons of parity or for other reasons. And you probably want to look at derivatives in that case. So it can also compute derivatives for M odd. Another interesting case is when the elliptic curve has complex multiplication, so it will be induced by some Hecke-Grossen character. And here, the symmetric power L functions, which I'll define on the next slide, these will be imprimitive and will split up as products of L functions of just the mth power of the Hecke-Grossen character. These will just be higher weight modular forms, so all be degree 2 L functions. So, for instance, psi cubed would be a weight 4 modular form, I guess. And one thing that it will do automatically, but obviously you can do it itself, you can do it yourself, is it can take these symmetric power values and it will normalize it into what the Bailenson or Bloch-Kato conjectures say. I guess Delinia wrote down things like this, but Delinia basically said that these were true up to a rational number, which is kind of useless for numerical experiments. So Bloch and Kato give an explicit basis, and essentially this should be like a central value, like in the Birch and Swearingen-Dyer conjecture. So you have an L value. These are periods. One of them is the real period, one of them is the imaginary period, and it switches depending upon the period I, about U, I mean. And on the right side, you would have something involving generalized Tamagawa numbers, generalized Tate-Chakravartis groups, generalized torsion things. If you had non-zero analytic rank, you'd have some sort of regulator also. So in some cases, Neil Dunnigan has done some calculations where you can actually construct these things and verify these, at least to things about powers of 2 with these generalized Tate-Chakravartis, etc. So, and this one is more like a Dirichlet's class number form, and that is at the edge of the critical strip and thus cannot vanish. So, and the conjecture is that these things should be rational with small denominator. So, I'll give some data near the end about that. Okay, so what are these symmetric power L functions? So this is the completely generic and this automorphic way of looking at how L functions should be defined. It's somewhat useless for the purposes of computation as far as I can determine. So I haven't even bothered to define it for Frobenius, but I have to add that if I really wanted to say what this was. So you have your L-adding Tate module and you tensor it up. So you have some sort of standard representation, so L is a prime that's not P, et cetera, et cetera. And basically what you're doing is you're taking the nth symmetric power of this two-dimensional representation. Well, actually, the nth symmetric power of the contrary gradient, I guess, because I've taken some sort of dual here. So this thing is the thing that you're interested in, and you have an inertia group here, which for all but finitely many primes will be trivial. So this will be a degree m+1 Euler product in general. And at the bad primes, you'll get some slightly smaller amount. Okay, so how can you actually compute this in practice? So here is the L function. This is something we can compute rather easily. We have the alpha p's, which are going to be the eigenvalues from the action of Frobenius. And we know that the trace of these is a sub p, and this is related to something that we can compute rather rapidly. That is the number of points on the elliptic curve over f p. This is true for good primes, for bad primes. I say this is degree 2, this is going to be of lower degree, either degree 1 or 0, depending upon if AP is 0 or not. It's some of the convenience that I wrote that. So the symmetric power L functions, here we have, for good primes, we have a degree m+1 Euler factor. So basically, we just take these things in all possible combinations. So here we have alpha p and alpha p bar. Here we would have, for the second symmetric power, we would have alpha p squared, alpha p bar squared, and one of each, one alpha p and one alpha p bar, etc. This is what this product does in general. It takes I of one and m minus I of the others. So the impetus for this project was a grad student at Sheffield, Phil Martin, who worked out what the Euler factors at bad prime should be. So I tried to do this at one point. I think Dabrowski tried to do this at some point in the 90s. So the previous literature was replete with errors. And now that we got a grad student to do things correctly, we could easily determine these bad factors. And this allowed us to do large-scale experiments. One can reverse engineer what these things are just by trying every reasonable possibility and see which one works. And this was actually what was done for a while. And there's only finitely many integers in the Vaj interval or whatever. There's only finitely many things that the conductor might be, etc. So what are these bad factors? For multiplicative reduction, so it's still a degree one thing. So at least the tame part of the conductor here will be m. For potential multiplicative reduction, similarly, you have a degree 1 thing for m1 and a degree 0 thing for m odd. For additive reduction, I've just listed the cases when the inertia group is cyclic.
Sorry, when you say potential multiplicative, do you mean non-split multiplicative, or?
I think it's the same. I mean, that just matters whether AP is +1 or -1, right?
No, I just don't understand the term potentially multiplicative reduction.
This means that
reduction, but negative, but non-negative.
Okay, so in that case, additive reduction means added potentially good reduction.
This should be potentially good.
I see.
I was writing these slides during previous stuff.
Yeah.
Yeah, sorry. Okay, so in this potentially good reduction case, I've only written the cases for you have cyclic inertia group, the exotic cases of p = 2 and 3. It's another chapter in this grad student's. Well, he actually didn't finish his thesis because his advisor got annoyed with him about not writing the proofs in sufficient detail. But anyway, so basically you just take some sort of periodic selection of these things. So that turns out to be not too difficult. There's a conductor. This is the symmetric power conductor. So the tame part here, at least, you can get via some sort of character theoretic calculation. Basically, you want to know the size of the subspace that's fixed by the inertia group here. So you can start with a two-dimensional representation of the inertia group, take symmetric powers about that, and to find the size of the subspace, you take its inner product with the trivial character. It's the standard representation theory fact. So this gives you the conductor, and the wild part was fortunately computed by Coates and Schmidt in an appendix to a paper about Iwasawa theory in the 80s. They were interested in the symmetric square, and their proof just is copied over. You get everything about wild conductors. Root numbers. So we do not know how, the root number is another one of these things that has this sort of definition that, well, actually the definition there is even worse, that is not very computable in practice. So we had no idea how to compute the root numbers at the beginning, but there's only two choices for it. It's +1 or -1. You just numerically test both of them, and whichever one works, that's what it is. Subsequently, we were able to go back, and now we can actually prove exactly what the root number is in every case. Once you have the root number for the first symmetric power, you can get the symmetric powers for the root numbers for all the symmetric powers. And the first symmetric power has already been worked out by Pulverstrand for 2 equals 2 and 3. For larger primes, it's much easier. Okay, so now that we have all this some theoretical background, so how do we actually compute special values of L functions? So I was at MSRI in 2000, and Watkins and I were talking about how to compute the modular degree of a specific rank 5 elliptic curve. And we were saying, okay, so, well, we know this is related to the symmetric square somehow. Okay, so how can we compute the symmetric square fast? And Henri Cohen is standing right there. He says, that's in the appendix of my latest book. Just look at it. You know? We have something like an n squared algorithm, and the one in this book is n. So I went off and implemented this. And this method is completely generic. All it uses is a functional equation that relates here s to n plus 1 minus s. So I've written down here, there's a sign in the functional equation. The sign will always be +1 when n is even, which is good. We came up with a fairly direct proof of this in the end. And here, this lambda is the completed L function. So you have the L function, you have some gamma factor, remember the little gamma of them, and you have something to do with the conductor. And the conductor here, it's the symmetric square conductor, some amount of 2 pi's, and then there's either a factor of 1 or 2, depending upon if you're even or odd. And this would be the square of C sub m. So C sub m will be essentially the number of terms that we need to take in a series approximation. So it's about size square root of the conductor. So this is the general idea. This comes from Hecke originally, had ideas about functional equations where you have a standard thing where you have some sort of integral and you cut it off at I divided by the square root of the conductor or whatever modular forms. So similarly here, I guess it was worked out by Laverne, except in more generality. So what are these gamma factors? These are worked out by Delenia in one of his papers. So here you have this one for odd things is just gamma of s times gamma of s minus 1, etc. For this one, when it's even, you also have a gamma of s over 2 things, so you can calculate the degrees of these gamma factors are going to be. Okay, so what is the computational method? You take these products of gamma functions, and you take some sort of inverse Mellin transform of them. So for the m equals 1 case, you just have gamma of s, and the inverse Mellin transform of gamma of s is e to the minus x. So that's quite easy. In general, you're going to come up with, so for instance, in the symmetric square case, you're going to get a k-Bessel function. You're going to get some sort of incomplete integrals defining these, and then you're going to get higher generalizations of these. So I've taken the L function, written it as a Dirichlet series. I've taken 2 points, kappa and lambda, that are related by the functional equation. And then to compute the deep derivative of the nth symmetric power at a point, well, if you just ignore this term here, this is the sort of thing that you would expect with the Dirichlet series. You would just plug in kappa there, and you have just this. Of course, you don't need to be in the regions of convergence. There's no reason for that to make sense. This is some sort of smoothing function. And once you've done the smoothing, well, then you want to relate this part to its reflection under the s goes to m plus 1 minus s map. So this relates bm n over n kappa with the same thing over n lambda. And there's, again, one of these functions. So this is known as an approximate functional equation. You worry about the signs of things, etc. So there's a parameter a, that a can be taken to be 1 if you want things to go fast. You can take a to be anything. The right side depends upon a and the left side doesn't. So this allows you to numerically check everything. You can do this for a equals 1 and some value somewhat close to 1, say 1.1 or 1.2, and compute this again on the right side. And you should get numerically indistinguishable results. And if you've got the wrong functional equation, you'll just get nonsense. You'll get things that do not coincide. Okay, so what are these sort of weighting functions? As I said, in the elliptic curve case, it's perhaps well known that it's going to be that's just the exponential function. Or if you want the first derivative, it's the exponential integral, et cetera, et cetera. So these things are variations of those. You can write them as, to say this is just rather brutally as a inverse Mellin transform. So with d equals 0 and m equals 1, you exactly have the gamma function for this. And the thing about these functions is that you only have to compute them once. These are independent of the elliptic curve. The only elliptic curve information comes in these coefficients here and these things with the conductor, etc. So let's say you want to do things with the 7th symmetric power. You just compute these things for the 7th symmetric power, however many derivatives you want. You compute these special functions once. It takes maybe an hour. Then you can take any elliptic curve and try to do the computations. So this is a do it once pre-computation sort of thing. So they say each of these sums, when you take a equals 1, you balance things essentially, and these things decay at infinity. So with m equals 1, you know how fast the exponential function decays. For higher m's, it decays slightly less rapidly, which prevents you from doing too high a precision. You can still get usually 16 digits of precision without too much problem. So you have some sort of rapidly decaying function. I guess that's all I wanted to say about this. And that means that each sum essentially only has this C of m terms, and this is the square root of m. And the last slide, when I talk about extensions, as I say, this is completely generic for any functional equation. It's been implemented in somewhat more generality by other people like Tim Doczynski and Mike Rubenstein. Okay, so here are a snippet of technical details. So how does it compute these f sub m of d functions in the first place? So Sympow runs a GP Paris script. It does it to maybe 150 digits of precision, and it pre-computes these to high precision. It just does it by taking a power series about x equals 0. You might have some logarithm terms you have to worry about. As you might know, this is a lousy way to compute e to the minus x. Taking e to the minus x as a massively canceling power series around x equals 0 is a bad way to compute it. It doesn't matter here because you're only doing it once. It then takes all these values and saves them. So for instance, at x equals 1, x equals 1.01, 1.02, etc., just saves a large mesh of these and the derivatives, and in real time, it just looks up these things and uses a local Taylor interpolation. So I think when Joe Buehler did a similar thing with the symmetric cube, he used some sort of Pade approximation involving, I forget, maybe the Legendre polynomials or something, but this local power series works fine. This works well because we only care about one point. I'm only interested in the critical values. People like Mike Rubenstein are much more interested in the zeros of the function. They have to evaluate this at many different s on the half line, for instance, to find zeros of it. And they need to be able to compute these generalized incomplete gamma functions on the fly. So their code is much more complicated. They have to worry about error bounds, etc. So the a sub p's, I wrote some code to do this. I think it's quite fast. It computes the a sub p's via a baby step, giant step method. And once you have these for the elliptic curve, as I had in the previous slide, you can get the coefficients for the higher symmetric powers. And then it uses this somewhat memory efficient way of summing up local contributions. And for instance, if you're computing the modular degree, an example that William gave earlier, you know that the modular degree is integral. So you can stop when you're within half, when you know that the error is less than 0.5, whatever integer you're closest to, that has to be the answer. Yes?
How does your computation of the AP for all p up to, say, 1,000,000 or something compare to Paris?
I think it's faster.
That's it?
Yeah, I think it is.
Have you ever benchmarked the two?
Well, I benchmarked it, but then I sent them my improvements, so.
Oh, great. Good job.
Okay, so here are some examples. So here is, take the 9th symmetric power of the elliptic curve 46a. So this is an odd symmetric power, should have a central value. It is this number, 2 to the 14th, 3 to the 10th. Factors of 2 and 3, it might just be a normalization thing, especially 2, when you have two different choices for the imaginary period, for instance. Then you get a very large square. And this fits well with the philosophy of generalized T-separators, so you should have self-dual motives in this case. For the 10th symmetric power of 44a, so here it's at the edge of the critical strip, you can note two things, that this large number here appears not to a square power. So here 5 is sufficiently small that it can appear to an odd power. But, here, this number is quite large and appears to an odd power. This is because the load of this dual with the same thing evaluated at 5 in some sense. M twisted by 6 and M twisted by 5 like this. There's also a denominator here that corresponds to some sort of generalized torsion group, I guess, in each number. So, of course, one of the interesting things when you compute all this data, obviously you're interested in cases where you have analytic rank bigger than 0 or 1. So here are some examples. I think these are somehow the extremal ones. So here is, as I mentioned earlier, complex multiplication is different. You can force funny things to happen just by having the root number switch sufficiently often. Here is one without complex multiplication. You take the 13th symmetric power of this, evaluated 7. So here's an example of a 13th power symmetric, of a symmetric 13th power L function that has analytic rank 2. And you can check this to sufficiently much precision that if you, how do you detect if a number is 0? Well, you have, as I say, this conjectural Bloch-Kato formula, and you know, essentially, basically you have to show that something would have to be less than 1, and then it's necessarily 0. We'll mention it again in the next slide. So this was also a strange one in that for 162b, both the 9th and the 11th symmetric powers have analytic rank 2. I think this is one of the few curves that we had 2 different symmetric powers for which we had this analytic rank 2. There's a lot of analytic 3 things wandering around, so I looked at Cremona's database for, I guess, the 3rd symmetric power. Here's a 7th symmetric power that's has analytic rank 3. I think it's the largest power we have. And Bieler, shown on top already in their paper, had an example of a analytic rank 4 thing for the 3rd symmetric power. So I think I've found something like 15 more of these. So their example was nice because they could actually construct things in the Griffiths group. They could actually find at least 2 independent things, I think, in this case. So all of their examples, though, they had to have 4 torsion, I guess, for the elliptic curve.
Excuse me. So what is a good point to switch from baby step, giant step to
Scope?
Yeah.
Something like 10 to the 18th or 10 to the 20th.
Yeah, that's exactly what I think.
Yeah.
It's way
Yeah.
beyond this.
Okay.
Yeah, I've done careful benchmarks with Perry, and it's exactly what you just said.
Well, I've been keeping careful benchmarks with Magna. So.
Wow, cool. They match up.
And I think the pre-scope is actually a little bit faster than Magna.
Yeah.
So. Okay, so what are the limits to this sort of methodology? So obviously you can only compute c to the m terms. This is the square root of the conductor. So something like 10 to the 9th. If D wants to do something like 10 to the 11th, I'm trying to dissuade him from doing this. So 10 to the 9th takes something like 6 or 8 hours. So how fast does the conductor grow? So at least for semi-stable curves, this is just going to be n to the m. In the wild ramification cases, if you notice these things where I did the 13th symmetric powers, these had large powers of 2 and 3 and other crazy things dividing the conductor. So you can just analyze how the conductor grows, and it turns out to be easier to get small conductors in these cases. So you can go farther for a given curve that has lots of wild ramification, it turns out. So what have we done? So for a 9th symmetric power, and all the ones below it, of course, just take the elliptic curves up to conductor 50, the even parity ones. So it's I say you need to compute to enough precision to get the Bloch-Kato number here. So on the previous slide, these Bloch-Kato numbers were something like, I don't know how many digits this is, maybe it's a 15-digit number, but ahead of time you know that certain powers of 2 and 3 will divide it. So you need maybe 12 digits of precision to get that. And as I said, for the 9th symmetric power, getting 12 digits of precision is not that easy. Convergence is somewhat slow. So, and I say when the main purpose of the paper was to look at Cremona's database as a large data set. So we looked at all of the curves in Cremona's database. It's a star on this because Cremona then went back and noted that he had actually missed some curves. So it was Cremona's database as it was at the beginning of this experiment. We looked at the symmetric cube for each of these. Of course, we looked at isogeny classes, not curves. and we computed each of the central values to 6 digits of precision. And this is enough to detect whether or not it's 0. If it looks to be near 0, you can then go back and distribute it to 12 digits. So the CM case, as I say, this is much easier to compute because the L function is in primitive, you can just split it into primitive parts. You can handle all these components separately. In some sense, if we were doing experimental mathematics, though, the CM case is not so interesting because there weren't just so many, there were more theorems in the CM case. So all we were doing is verifying theorems. It isn't as interesting as trying to get conjectural evidence. So how can you extend this? So this is an object, L is symmetric squared E at 3. So Mestre and Schapacher looked at this thing, some sort of Kronecker series, then more likely involving polylogarithms, Goncharov and Levin and Gongol and Zagier, such relations to K-theory. So you could also have a symmetric cube here and take other integer values. It becomes more and more difficult because you have to compute more difficult regulators, with polylogarithms, etc., to come up with the actual interpretation of these. Computing the L value, though, all you would have to do is to change the inverse Mellin transforms that I had. You just shift them, and they say, for every single symmetric power and place in the complex plane that you're interested in, you can just compute these once. And then you can, for instance, run over all the elliptic curves in the Antwerp-4 tables or whatever. So this sort of thing probably can be done now. I think this one would be FRG equals. Okay, that's all I have to say.
Any questions?
So I guess I missed what you were saying about the block calculator. We know how to compute everything to guarantee that the number you're checking is pursued an integer. Is that correct?
Oh. No, we don't know how to do that.
So but you said something about the number being less than 0.
So when I say here, 6 digits to detect higher analytic rank. So the things that it is close to 0, well,
no,
then...
I'm not talking about 0. I mean talking the non-zero case.
Oh, the non-zero case.
You were just saying this is what the Bloch-Kato conjecture would predict.
I'm saying that I computed the Bloch-Kato number that I listed before. There's this ratio of an L function and its periods, and I got this integer.
But there's some stuff that goes into it that we don't know how to compute. Is that correct?
Yeah. We don't know how to compute the right-hand side of things. I mean,
so I'm just asking, when you're computing, you already have a presumption that is an integer, or you don't?
No. I mean, I computed this to enough. I mean, you can bound the denominators. So, I mean, the only thing that goes in the denominator, just like the BSC, the only thing that goes there is a torsion group.
So you can bound that?
Yeah. You can bound that. Question?
What's the relation? How large does P need to be to get a certain level of precision, or what's the relationship?
It depends upon, so.
You're not assuming the Bailenson conjecture?
I don't know. So, as I say, there's some sort of decay of these special functions. And basically, you want to sum up until these functions become small. So, with an exponential function, you get some sort of linear convergence. But for instance, if your C of M was something like 10 to the 5th, once you got n up to 10 to the 6th, then this sort of e to the 10 to the whatever power should be fairly small. So, it should be some linear distance past C of M, which is the square root of the conductor. So that's how many primes you need to compute. This is how it's usually phrased. It's just that, well, you just need to compute square root of the conductor.
Any more questions? Okay, let's thank you for that.